Okay, I've left little wet smudges where I had arrows over the V1, V2, U1, U2, but all being squared here. You can't square a vector. You can take its dot product with itself, you can square its magnitude, but you can't square a vector. So the arrows were completely misplaced on these velocities here. Okay. Now again, now this reads correctly. We do have the arrows here because momentum is a vector quantity. These equations express again conservation of energy, conservation of momentum in an isolated system consisting only of two interacting masses. Now, that set of equations is completely equivalent to this set of equations, which is a much easier set to work with. I haven't proven it, but it's not that hard to prove, just a matter of algebra. Treat these as simultaneous equations and do a few steps and you get to this. Okay, and this says, well, momentum is conserved. And this says that the relative velocities before collision are equal and opposite to the relative velocity of the two masses before collision is equal and opposite to the relative velocity after collision. And this is completely equivalent to this, saying that, and good heavens, okay, there's supposed to be an equal sign here and a negative over here. I had the negative, but I didn't have the equal sign. This is equivalent to saying that the change in the momentum of the first object is equal and opposite to the change in the momentum of the second. Now this equation is completely equivalent to this equation. And then the second equation is the same as this one. So this set of equations, this set of equations, this set of equations all say exactly the same thing in slightly different form. This is the set that I think you're best off to start with in a case of what we call an elastic collision, a collision where kinetic energy is conserved. Okay, this set of equations is directly related to the impulse momentum theorem, which says that the change in momentum is equal to the impulse in an interaction. And this is a direct consequence, again, of the fact that when two objects collide, they exert equal and opposite forces in each other for the same time interval. And that leads directly to this, which leads directly to this. Energy conservation is energy conservation, but in conjunction with momentum conservation, you can replace the energy conservation equation with this, which just says the relative velocities are equal and opposite. And what this says is that when the two objects come together, they have some relative velocity. When they go apart, they have some relative velocity. And those relative velocities are equal and opposite. So if you're in one object and you're looking from your point of view, you see the other object coming at you and then receding with exactly the same velocity, exactly the same speed, but in the opposite direction. So those are very important characterizations, and you would do well to understand this first, understand how to use this, and understand that this is an expression of this. Energy is conserved, momentum is conserved.